The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. Yo-ho, it's hot. The sun is not a place where we could live. But here on Earth, there'd be no life without the light it gives. We need its light, we need its heat, we need its energy. Without the sun, without a doubt, there'd be no you and me. The sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. The sun is hot.
It is so hot that everything on it is a gas: iron, copper, aluminum, and many others.
The sun is large.
If the sun were hollow, 1,000,000 Earths could fit inside, and yet the sun is only a middle-sized star.
The sun is far away.
About 93 million miles away, and that's why it looks so small.
And even when it's out of sight, the sun shines night and day. The sun is
So that is They Might Be Giants telling us a little bit about our sun. But let's take a look more scientifically at some of the properties of the sun. The surface that we actually see is called the photosphere of the sun. If you could look at it very closely, it would appear to be granulated, not really one solid surface, and of course it isn't a solid anyway, but it wouldn't look completely uniform in color. You could think of these granules as little bubbles that rise up in, say, like a pot of water, rising to the surface and transporting energy to the upper layers of the sun. Here are some more properties summarized in this chart about the sun. And so what allows the sun to stay roughly the size that it is? Well, it's in a balance, a state of rough equilibrium between the force of gravity, which would like to crush it all towards its center, and the pressure which flows outward from all of the energy of the nuclear reactions in the core of the sun. This balance goes on for billions of years until, as we noted with stellar evolution, eventually the sun, like other stars, will run out of its nuclear fuels in the core, and this balance will be upset. As you go deeper into the sun, the temperature becomes hotter and hotter, and it becomes denser and denser, just as you might expect. This cutout shows the various layers of the sun. The core is where the nuclear reactions are taking place. The radiative zone is where the energy is being transported from the core to the upper layers of the sun's atmosphere. In the convective zone, radiation is no longer the most efficient means of heat transport, so convection takes place there instead. And then we have the photosphere, which is the surface of the sun, and that convective action that is taking place results in that granulated surface that we see. That is followed by the chromosphere, which you can think of as the sun's lower atmosphere, and the corona is the thin outer atmosphere that you can really only detect during a solar eclipse because it's so tenuous. At each layer, there's a rough hydrostatic equilibrium taking place between the outward pressure and the inward pull of gravity. So the more rapidly the atoms or molecules move in a gas, that results in a higher temperature. And the cooler the gas is, then that corresponds to atoms moving more slowly. So if we take the density of the substance of the gas and multiply it by the temperature and a constant, we will be able to come up with the pressure of that volume of gas. And so going back here then, the pressure, these blue arrows indicate, the length of them indicate the rough pressure at that point. And so you see that they are roughly balanced by the inward purple arrows that are the pull of gravity. So what's interesting is that when a photon is trying to make its way from deep inside the sun, to the outside and escape the sun, it executes what is called a random walk and through the radiative zone, and eventually it will reach the surface of the sun, but because it will bounce off of so many different rapidly moving atoms in the process, it actually takes it thousands of years, 100,000 years about, to make its journey from the interior of the sun to the exterior of the sun. We will learn about a particle that, unlike a photon, however, can basically unimpeded make it from the core of the sun to the surface of the sun without taking years for this to take place. We'll get there in a moment. So the chromosphere and the corona can be seen easily during solar eclipses, and I would caution you when I say seen for any of these things, whether I'm talking about the photosphere or during a solar eclipse, the chromosphere or corona, you would never want to look directly at the sun. Either during a solar eclipse or at any other time, you don't want to look directly at the sun unless you are happy with suffering some damage to your vision and possibly blindness as a result. But you can observe the chromosphere and corona of the sun during a solar eclipse indirectly, and of course we can look at the sun indirectly as well. And so indirectly observing the chromosphere and corona during a solar eclipse reveals that this part of the atmosphere of the sun is actually extremely hot, but it's very thin. That's why we don't see it under normal circumstances. There's also lots of churning and bubbling going on at the surface of the sun, lots of activity. Some of the activity involves matter from the sun following magnetic field lines, such as the corona holes, and also there can be flares and mass ejection events that take place on the surface of the sun. Mostly we hear about these when they interfere with our satellites and cellular communication as a result. Okay, so let's get back to this source of power, these nuclear reactions that are taking place in the core of the sun. What exactly is happening here? So the type of nuclear reactions that are taking place are known as fusion reactions, not fission reactions. Fusion involves smashing nuclei together rather than breaking them apart. In doing this, you can convert mass into energy, and you get tremendous amounts of energy in the process by Einstein's famous equation E equals mc squared. The reason this energy comes out is that when the fusion takes place, there's less mass going on, and so that mass has been converted to energy. In order to get a fusion reaction to take place, you need a couple things. First, you need very high temperatures so that the atoms, or really they're just nuclei in this case, are moving very rapidly. That allows them to have a lot of momentum, and then also you need a lot of pressure that sort of pushes them together. So when you have very high temperatures and pressures, then fusion reaction can take place, because these nuclei of hydrogen, which is basically just a proton, because hydrogen consists of one proton and one electron. This fusion reaction, these protons, they would normally want to get away from one another because they're both positively charged, and so there's a repulsive force, electric force, that makes them want to stay apart. However, fusion forces them together, and this is accomplished by the rapid speeds and high pressure taking place in the core of the sun. So here's a schematic which summarizes the chain of nuclear reactions that take place. You won't be held responsible for knowing the details of this, but it's interesting to look at some of the products that we end up with. You start out with your two hydrogen nuclei, and they fuse together to form basically a heavy hydrogen nuclei, H2. And then hydrogen, that will find a single proton by itself eventually, and then those fuse together to form helium out of that process. It takes a few steps to get there, but you end up with, out of the process, you end up with helium, and then also hydrogen goes on to interact with another hydrogen atom. Some byproducts that are produced in this process are gamma rays, which is basically a photon, positron, which is a positively charged electron, and a neutrino. The neutrino is this interesting particle that I'm telling you can just make its way from the center of the sun to the exterior of the sun without having to be stopped along the way like the photon is. So since neutrinos are a byproduct of the nuclear reactions taking place in the core of the sun, at one point people decided that we ought to try and measure the neutrinos that are coming from the sun in order to confirm whether our model of what's going on in the core of the sun is correct. But it's a little tricky because detecting neutrinos is very hard. If they can get through all of that high density and temperatures inside the sun, then how could we possibly hope to detect them on Earth? Well, it's complicated, and we'll go through this. But when we first started looking at this question, it turned out that there weren't as many neutrinos as we would have thought. And so this was referred to as missing neutrinos. And people didn't understand why this was. Did we misunderstand what was going on in the sun? Was it our detector? What was happening? So first of all, what is a neutrino? It's a type of subatomic particle, and we don't really need to know the details of this, but it's of neutral charge. That's thus the neutr in neutrino. They are practically massless, although not entirely massless. And as I mentioned earlier, they do not interact very strongly with matter. They're able to just go nearly the speed of light through just about anything. Your body, a piece of lead. It's very difficult to stop a neutrino. And neutrinos come in what we call three flavors. They can come in what we call an electron neutrino, muon neutrino, and a tau neutrino. You don't really need to know the labels of these, except to say that there are three flavors, and this was actually important in solving the mystery of why there were not as many neutrinos as we thought there would be. So in order to detect these things, what's needed is basically a huge pool of some kind of fluid and patience and a way of detecting the rare event of when a neutrino actually does interact with matter. And so by doing this, I'm not going to go into the details of how these detections take place, but it was found that there were not as many neutrinos as we expected. At neither one of the first couple experiments designed to detect these neutrinos. So a couple explanations that were posited for why there weren't enough is that perhaps our solar models were incorrect, or perhaps our understanding of these particles, these neutrinos, were incorrect. Or is it possible that we were looking for a specific flavor of neutrino, but maybe in the process from going from the sun to the earth, maybe the neutrino could change flavor, and that therefore the flavor that we were looking for we wouldn't have as many of because some of them changed to a different flavor. So here's a couple different observatories that were used to try and detect these neutrinos. Well, one of the first ones actually. And so this neutrino detector was able to tell the difference between the total neutrino flux and that of just the electron neutrino, which is the flavor of neutrino that we thought was coming from the sun. And so the total of all the flavors was actually consistent with what we thought should be coming from the sun. And so it turned out that actually these neutrinos were changing flavors in the process of their travel from the sun to the earth. And so it wasn't that any of them were missing, it's just that they changed flavors in the process. And this is what is referred to as neutrino oscillation. So the important thing to keep in mind about the neutrino, the solving of the mystery of the missing neutrinos, is that it basically confirmed that what we thought was taking place in the core of the sun actually is taking place, and that our models for the nuclear reactions are correct. And so going out to the surface of the sun, let's look at some of the activity that's taking place there. There are things called sunspots, which you might be aware of, that are actually just simply cooler regions on the photosphere of the sun. They're associated with magnetic fields, And so sometimes you'll actually see the matter going in a loop like this around the magnetic field lines. And it's not important to really understand the whole electricity and magnetism that's taking place here, but think of it similarly to how the Earth has a magnetic field. This is just a local magnetic field that gets a little bit entangled, and the particles then travel along these magnetic field lines, creating loops and possibly ejection events. Solar flares can also happen, and you've probably heard about these before. And coronal mass ejections are huge ejections of material from the sun. And here you see an image of this taking place. You see just how large of a region this mass takes up when it's being ejected from the sun. When you have a coronal mass ejection like that, then you can look forward to the northern lights, because all of those particles are eventually going to hit our magnetic field if they're pointed towards us. And in that process, then they're going to interact with the atmospheric particles and create what we know as the northern lights. The sunspots do not remain constant over time, the number of them. They actually go through a period of about 11 years where they go from having a lot of sunspots to not very many, to a lot again to not very many. And this is pretty regular and has been observed throughout time. Here's a timeline of basically the number of spots on the y-axis and then the year on the x-axis. So this is going back all the way to 1860. You can see this regular pattern arise. And of course the peak is not always going to be quite the same or take place at the exactly 11 years, but it's roughly that, pretty closely. And the peaks may range in how large they are, but they're still obvious if you plot it like this. Just like Jupiter and Saturn and the gaseous planets, the Sun has differential rotation, which means that the rate of rotation is not the same as you change your latitude. So basically the equator is rotating faster than a point near the pole. And so this is why is thought that that there is this change in sunspot activity, because when the sun is doing this differential rotation, then the magnetic field lines, which on Earth are just nice, neat lines, they get twisted by the fact that different parts of the sun are differentially rotating at different speeds. And when there is some anomaly in this regular expected solar cycle, then sometimes it could affect the climate. The Little Ice Age in the last part of the 1600s and early 1700s is correlated with a period of very little solar activity. And so sometimes you can chalk things like this up to what's going on with the sun, just because I feel I need to say so, going back to what we talked about climate change earlier. This isn't to say that this hasn't been accounted for in climate change models, because it has been. So if you hear people say, well, it's the change of what's taking place in the sun, that has been accounted for in every model that climatologists use.